the thermochemistry unit, so this will take me through the rest of the PowerPoint and the rest of your guided notes. So let's go back and review a little bit. We were talking about thermochemical calculations last time, and we ended with talking about what do we measure this when. Again, it's joules and calories. Specific heat, the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. And of course, our calculations, Q equals M delta T C. Our calculations for determining specific heat or heat energy. C being specific heat, Q being your heat loss or gain in joules. Delta T, the delta meaning change in, T meaning temperature, and of course M, mass measured in grams. Those are our practice problems. All right, let's talk about chemical kinetics. Let's talk about reaction rates. I want you to look at this graph for a little bit, and this may be a little confusing to you, but bear with me. Think of this as a time-lapse graph. When you put materials together before a reaction starts, the red and the blue being your products, the green being your reactants, you should have all reactants and no products. As your reaction progresses, you'll notice that your reactants fall and your products rise as your reaction moves toward completion. Now this can be a long process or it can be a short process, and we'll talk about reaction rates in just a second. A couple things you need to know about, I guess we'll talk about reaction rates right now. A couple things you need to know about reaction rates. They can measure the disappearance of your reactants. You can use that to measure how quickly what you started with is going away, and that would be this green line right here. The second thing, it can measure the appearance of your products, this blue and this red line. How quickly are you getting NO and O2? You can determine that through your reaction rate, and unfortunately, I know you guys take this, they are proportional stoichiometrically. Stoichiometry is important here. And this balanced equation is significant in determining your reaction rates. Now, we're not going to spend any time calculating reaction rates as it stands right now, unless we get some extra time in the future, and then maybe we'll just have a fun day and calculate reaction rates. Not fun. Okay, the reaction mechanism. We've looked a lot at chemical equations, and we'll go back a slide. This right here is your chemical equation up at the top here. Your reaction mechanism is a little different. Your reaction mechanism is the series of steps that occur to get through a chemical reaction. So for instance, let's say you are baking a cake. You start with your reactants being flour, milk, eggs, sugar, vanilla, pinch of salt, or baking soda. Probably missing something. Flour, did I say flour? Probably flour. Those are your reactants. Your product is cake. Your reaction mechanism is going to be the recipe. It's the steps that you follow to get from what you're starting with to what you're ending with. Now, when we look at a chemical equation, we don't ever talk about the reaction mechanism. We just say, here's where you are, here's where you're going, and we don't look at those in-between things. But those in-between things exist, and they are important. You'll find later when you take college in chemistry in college. Chemistry in college. Your reaction mechanism, that's what I just said. Your chemical equation does not tell us how the reactants become products. It is a summary of the overall process. Your equation is the summary. And here you go. You've seen this before. We know what this yield sign means. That sign represents the reaction mechanism, even though we don't actually talk about what the reaction mechanism is. That's symbolizing the fact that we have to run through a series of steps. Okay. Does not tell us the steps. Let's talk about the rate determining step. The rate at which you can create something or go through a chemical reaction is determined by your slowest step. For instance, let's say you and your friends are out passing bricks along to build a house, right? And so you guys set up like a conveyor line. Your friend passes you a brick, you grab the brick, you pass it to your next friend, and you continue down this line until you've got a giant pile of bricks. But let's say your enemy over there, Johnny, is really slow at passing bricks. And so when he gets a brick, we're just going to pretend this is a brick, he gets a brick, instead of passing it like a normal person, he goes as slow as he possibly can. Oh my gosh, this brick is so heavy. Johnny is your slowest step. The rate at which you can pass bricks is dependent upon how quickly Johnny can pass his bricks. Because you can't pass the brick to Johnny when he already has a brick in his hand, and the next person in line can't pass a brick if he doesn't have one. He's still waiting on it from Johnny. So your reaction rate is determined by your slowest step. Okay, factors affecting rate. The first one that we're going to look at is temperature. As you increase the temperature, you are always going to increase your rate of reaction. We talked the other day about collisions, how you have to have the proper energy. Set that right there so you can see it. The proper energy, you have to get into the bucket, and you have to have the proper orientation. So as you increase your temperature, not only do you increase the energy of the molecules, but you also increase the number of collisions, which means you're more likely to get that collision with the right orientation. So of course you're going to increase your reaction rate. Surface area, we looked at this in solutions. As you increase your surface area, you increase your rate of reaction. That's because you have more solute-solvent contact. Okay, concentration. Increasing the concentration usually increases the rate of reaction. However, if you increase the concentration of the wrong thing, you can actually force your reaction to go in reverse. But generally, if you're increasing the concentration of your reactants, your reaction will continue to progress towards the products. All right, the last thing is the presence of a catalyst, and we'll go ahead and move to the next page there.
Look abnormal too.
Okay, a catalyst is a substance that speeds up a reaction by lowering that reaction rate, or that, not the reaction rate, lowering the activation energy. So essentially, it's like saying, I need you to roll a bowling ball up Mount Everest, but then I'm going to be a catalyst and I'm going to actually shrink Mount Everest. We're going to pull that activation barrier down. And you'll see that it's the graph on the very bottom of your page, and we'll look at that in detail. You also have enzymes, Bryce. Large molecules, usually proteins in your body, that help catalyze biological reactions. If you didn't have these enzymes, then the reactions that you need to have happen in your body wouldn't happen, and you'd die. That would be sad.
Biological father.
Now I switched these on your page. It says heterogeneous first and then homogeneous. So go ahead and hit that one more time. We're going to look at heterogeneous catalyst first. A heterogeneous catalyst is present in a different phase than your reacting molecules. So if you are reacting two gases, your heterogeneous catalyst would be a solid. Or it could be a liquid, but we'll say it's a solid. But it's not in the same phase, because hetero means what?
Different.
Different. Good. Hetero means different. So we need something in a different phase. The other type of catalyst you can have, obviously, is a homogeneous catalyst. What does homo mean?
The same.
Same. That means that you are present in the same phase as your reacting molecules. Jose is reacting two liquids. He's using another liquid as a catalyst. That means that liquid catalyst is then a homogeneous catalyst. Okay, so here's your exothermic reaction. This is the chart that shows what it would look like if you have a catalyst. Again, you're storing your energy here in your reactants because the energy of your products is lower, which means this reaction will feel what? warm to you because it's releasing energy out. It's pushing energy out. If you're holding it, it's pushing energy into your hands. This is what I meant by making Mount Everest shorter. That catalyst pulls down that activation energy, meaning that you need less energy to get up over the activation barrier. Okay, let's go ahead and we'll go back a slide. Here's the last thing on here. Here's your endothermic reaction. Again, your energy in your endothermic reaction is going to be stored in the product, so it will feel what?
Cold.
It'll feel cold because you're putting more energy in than you're actually getting back from the system. The thing for you guys to remember about a catalyst is that your catalyst is not going to be in your reactants or your products. It's going to be part of your reaction mechanism. So when we write out our reactions, you're not actually going to see the catalyst there, unless sometimes they'll put it over the yield sign, but generally we just leave it out. That's it for thermochemistry. Questions? Right, I'm going to edit this silence out. Just tell a joke. If I had any jokes, I'd tell a joke.
No, it may probably make it worse.
My favorite joke is the, what do you call a fish with no eyes?
You already saw that one. And I saw that on
That's my favorite joke.
I saw that